Andreas Zeller. I'm the author of the Debugging book, and I'm here to present you a new chapter.
The recording here, and we are sort of live and we are recording. Okay, great. Okay, folks. Well, I already said it. Happy New Year to everyone. So I can't see you right now, but I hope you are all happy and sane and everything. And yes, we are transmitting live from my office in the Cisco building rather than me sitting at home from for some virtual background. I can put up a virtual background if you prefer that, but this is actually my sort of, well, this is my living room. No, this is not my living room. Well, it's sort of my work living room or work room or whatsoever. Okay, we're in for quite a treat today. It's going to be a beautiful, there's going to be a couple of beautiful findings from automated debugging. We're going to see today, today's topic is automatically tracking the origins of failure, which is a pretty cool, technique. But before we get to that, let me first start with a couple of Q&As, question and answers, in particular regarding the project, but also regarding the course. So feel free to post them again in the questions and answers field of Zoom. And we also have some open questions from the forum, as I understand. Johannes, what's the current status over there?
So I answered the questions this morning, but there is basically regarding group work. So for the second project, there is no group work. It's an individual project as opposed to the first project. But there was a follow-up question that the student wanted to know. So they already started working in a group and they wanted to know whether it is okay to take the rough skeleton they already have and continue solo from there, or whether they have to start from scratch.
Please be totally transparent about that you have been working on some skeleton in the beginning, and we will consider that. So, but make sure that that if this skeleton makes more than 10% of your final work, then you will be in some trouble. So be sure to keep the common skeleton that you're using to a very minimum. Okay. I hope that's a sufficient answer. So I don't need you to throw away everything, but say anything you can carry over in terms of thoughts, okay, rather than code is good. If there are things that you carry over in terms of common code, that's not good, okay? And generally do not work. So this is supposed to be, in here you're supposed to work as individuals for that project, so please do so.
Okay, yeah, but this is it from the forum.
Yep, this is it for the forum. Okay, good. Yeah. So, okay, let's switch over to our correspondent in New Delhi. New Delhi, do you have any? Oh, I'm afraid New Delhi isn't here today at this moment. I'm so sorry. Okay, our correspondent from Brazil is not here either. So we will be stuck with the situation in Saarbrücken for the moment. So please bear with us for a moment longer. Okay, if you have any questions regarding the course or the contents, please feel free to put this into the Q&A session, into the Q&A window. Okay, when will the results of the first project be published? Ah, finally a question. When will the results of the first project be published? The answer is soon, because we already have the results of the first project. Johannes, is that correct?
Not for all of the students, but for most of the students, we already have the results. So we need to basically finalize the results.
So we are working hard day and night in order to deliver that to you. I feel like a TV moderator. Maybe the background changes of things here. Okay, let me switch over immediately to the contents of today's lecture or today's chapter, which actually can be rather quick because it's a concept that is not too complicated. It is complicated to implement, but fortunately I have done all of this for you already, and you can look at this from a pure usage perspective. Okay. So welcome to our material today. The topic today is tracking failure origins, and let me share my screen right away. I hope this all works. Who can share? No, that's not what I wanted to do. We are talking about this thingy here. Okay, Johannes, you should be seeing my screen now with seeing tracking failure origins. Is that correct?
Yes. Yes.
Wonderful. Do you see anything else? Any compromising emails?
Nope.
Students reports whatsoever?
I don't think so.
Okay, wonderful. Okay, good. So today's topic is tracking failure origins, and that's a fundamental part of debugging, namely to figure out where an individual value came from. We're going to look at this using a well-known example. We're going to look at this using the middle program, which we already have been looking at with when we were talking about statistical debugging. Just to remind you, here's the middle program in all its glory. The middle program is a program. This is actually, people ask me, where does this come from? This is actually a standard example in automatic debugging approaches. And this was introduced in the Tarantula paper by Jones, Stasko, and Harold. How many years ago was that? You can look this up in the chapter on statistical debugging. This is an example which they use to point out the benefits of statistical debugging. And this program is a program which is supposed to return the middle of three numbers. So it takes X, Y, and Z, and you can easily put in here middle 1, 2, 3, for instance, and then it will happily return 2 as the middle of the three numbers. So that's not very surprising. But there are also circumstances where this does not work. If you put in middle 2, 1, and 3, for instance, then you get the number 1. And pardon my limited math understanding, but I can tell. But 1 is certainly not the middle number between 1, 2, and 3. It's actually the minimum of the two. The middle of 1, 2, and 3 is 2, as we have seen already up there. And now the question is, whenever you're counting such a thing as a debugger, as a programmer using debugging, the question is, where does this value come from? And in order to answer this question of where does this value come from, we are taking a look at the program ourselves. So can make this still a bit larger here. So let us see this in all its glory. So to start with, this program sucks a bit because we have all these many return values in here. And this is unfortunately one of the downsides of having multiple exit points from a program. You don't know which one is which. So I'll make this short. You can actually start you can actually go and start a debugger here, an interactive debugger, and then find out which one it is. And then you will find out that the actual value returned in here is the one in the first statement, if I recall it right. Oh, we're going to find this in a second. We're going to find this out in a second. And but even if you have found out which actually of these many return statement it was that actually got us here, the question is then, why did this come to be and how did this come to be? So we know that the value returned, so apparently this is y, actually came from the y parameter up here. So this is how it was passed. But the question is, why does it come to be? Because there's also a couple of conditions in here that govern the whole thing. And when analyzing programs, we distinguish two kinds of such influences of individual statements and their variables on other statements. We distinguish data dependencies and control dependencies. A data dependency means that a point of data, such as y in here, comes from another variable, which happens to be the variable y up here. Okay. A control dependency, however, means that there is some other statement in here which controls that this statement was executed, which in this case was y is less than z and x is less than y. Okay. So the big question is now, so these are things that we normally do in our minds when we are exploring programs. And this is also something that we build a mental model of how all these statements and values influence each other. And this mental model is actually also known as a slice. We create a slice of the program that actually has an influence on our final output. And this concept of slice was introduced by a guy named Mark Weiser almost, I think this must have been in '82. So this is almost 40 years ago, imagine that. This concept of a slice of a program, meaning that we're only looking at a small part of the program that actually could have influenced the effect that we're seeing, is something that has been carried over into debugging. So normally, when we are trying to figure out where such an individual value came from, where does this one came from, where does this two came from? Well, we look into the program code and we're just all trying to understand where these things come from. And we're looking at these individual values, we're tracking back their dependencies, we're finding out that this Y comes from here, and this return statement here was controlled by this if and this other if. So this is something we do implicitly in our minds. And when we're doing something implicitly in our minds, this is all nice, but there's two risks to that. One risk is that we may actually do a mistake because we may get the scoping rules wrong. We may actually forget to look into particular influences and like things. And the second thing is that building such a mental model in our minds means that we have to stick to it. We cannot stop debugging while we are still having this mental model in our minds. So, because when we stop debugging, then all the mental model goes away and we have to reconstruct it again and again. So one interesting idea is to actually make this mental model of dependencies explicit, thereby providing a help to debuggers, to human debuggers, figuring out where individual values came from. And tools that do that, giving you such a mental model of dependencies within the program, are called slicers. Slicers because they take away a slice of the program which has the most influence on the effect. To cut a long story short, I'm going to show you a slice right away because I have implemented a slicer for Python that actually builds precisely such a set of dependencies and which allows you to show where individual values came from. And this is actually pretty easy to use. So we do, as usual, we do from slicer, import slicer, here we go. And we have imported the whole thing. And you use it, as you already have seen, with other parts of our course. Use it with a slicer as slicer, and then the code that is contained in the with block will actually be sliced. However, our slicer requires that we also provide
Andreas?
Yeah, I'm hearing you.
I don't think we see what you are typing. Now it updated.
Okay.
Well, that took quite a long time, but now we are with slicer. So.
Okay, we are with slicer. That's where we are supposed to be.
Okay.
Okay, good. So I'm still typing, and you can hear me typing, and it should be updating now. The place I'm in right now should actually have the best connectivity anywhere in this town. So let's see how this works. So what we are doing here is we are providing the name of the function that we want to slice, because this actually internally requires to instrument the function before it's being executed. We'll get to that in a second. So let me show you right away what a slice looks like. So we slice the whole thing, you don't see anything, but now if we want to see, but then we can actually view the slice by simply entering slice at the command line. Yes, what is it?
There is another problem. Now your voice is a bit unclear. A lot of change put it nicely. It sounds a bit like you were underwater and trying to talk.
Underwater, you say? Okay.
Yeah. It's a bit muffled.
I can also change the microphone if you prefer that. Let's see. I can certainly change the input volume if that's better.
I mean, you are clearer, but your voice is clearer, but now it sounds a bit strange.
Okay, well, whatever is going on here, once you go to another place, everything changes. Okay, let me switch over to another microphone. So how does this sound now?
It sounds better, but it's very low volume. So maybe.
Okay, I can crank up the volume. Is that better?
Yeah, that's better.
Okay, so I'm using another microphone and we're cranking up the volume. Okay, here we go again. For the fun of it, it's good that we have backup microphones. I have 1, 2, 3, 4 microphones here I can use. Okay, let's use this one for a check. Okay, good. So now that I think apparently all our technical problems are resolved for the moment, let me show. So we have now computed the slides, and now let's go and see that. And when we see that, it actually is shown as a big graph. Let me reduce the size in here. And this graph contains all the individual variables at various locations in the program and shows their dependencies. What we have here at the very end over here. So this is the return value that we're seeing. And we can now follow back these black arrows to see where does this value, as shown here as y, actually came from. Yeah, and we see that this comes from the value of y as it was passed as a parameter. Okay, so these black lines here in the graph show data dependencies, and you can we can say that the lower ones here, the ones being pointed to, they depend on the earlier values, but we can also interpret this graph as a flow graph. The value, as we have it up here, flows along the direction of the arrow into the value found below. So this is a data dependency. And the second kind of dependency we're having in here is, the second kind of dependency we are having in here are these dashed arrows, these gray arrows. These are control dependencies. A control dependency tells you that here's another value, here's another variable which controls whether a particular statement will be executed. And in this case, and we find that there's actually 3 tests that were being taken. There's if y less than z, and if x less than y, and if x less than z. All these 3 were executed. And all of these 3 actually influence that this return statement has been used. So this return statement was executed because of all these tests, which actually all in turn also have their dependencies to x, y, and z. And and the value that is being returned, the value of y, this stems from up here, from the value y as it was passed over to middle. So this is an explicit representation of the mental model that we build when looking at the code of middle, where we find out how do all these things fit together, and this is a more explicit way of viewing these things. The nice thing about being able to produce such a graph automatically is, of course, that if you have any dependencies in there which you weren't aware of, well, all of a sudden you're going to see them. So if, for instance, there is some weird constant somewhere else in the code that influences the whole thing, keep in mind middle is just 10 lines of code, so this is really simple. But if there's something that is far away, yes, you will be able to see all the dependencies. At the same time, and this is the advantage of a slice, there's plenty of statements that are not included in the slice, and therefore you don't have to consider them as it comes to your code. We can actually also visualize these dependencies in the code. There's a special command, slicer.code, which gives you a listing of the code as we have it up here. And this listing is annotated with 2 things. First, we have these little stars up here, and these stars are all the statements that are part of the slice of the. That means these statements have been executed and they have had an influence on our final value. And the second thing is, you can see these annotations. This code command adds special commands in here and tells you where individual values came from. So this return y here, you can see in the comment, it sees that the value of y comes from y in line number 1, which of course is the definition line here. And you also see, so this is a data dependencies showed with this double arrow. There's also single arrows which point out control dependencies. And this says that the execution of this statement is control dependent on the test in line 5, which happens to be this test of elif x less than z. Okay,
So this allows you to look up these dependencies right within the code. So you can wonder, okay, where does the value came from? Well, you already see the one return statement where it came from. It must be this one because the other ones weren't executed. Now you wonder where does y came from? Well, y is the y as it was originally passed. And you can look up which test this was, test in line number 5, and this was this test. And this test takes the x and z from line number 1, whereas it also depends on the test taken in number 3. And this is how you can then walk back all the dependencies in your mind in order to figure out where a particular value came from. So the question is, the big question might be at this point, how on earth do we actually produce such a graph? And how do we get all these dependencies from an existing program? And well, there's a whole chapter for you to read on that, but for good reasons, most of this chapter is actually marked as so-called excursions. So that is, there's plenty of code parts which are optional to read, but the main point is that what this program does, what this slicer does, is it actually instruments the code and then tracks all the accesses to variables and all the settings of variables. So because if we can track that the value of y up here, down here, actually comes from up here, then we have a dependency in here. So how does this work? Well, we can turn on logging, and this logging will show you something that is pretty revealing and shows you what the instrumented code actually looks like. And you will be shocked to see all that. This is an amazing amount of things in here. So this is what Slicer does with your code before it gets executed. And there's quite a number of things in here. So let me just show you a few of them. So we have a tracker, a dependency tracker, which is named _data. So keep in mind, again, this is the original code up here, and this is the code that comes out as it's being instrumented. So we do have a dependency tracker, which is _data in here, and this dependency tracker has a number of methods, and these methods actually track dependencies as they exist. So first thing it does here is it says, okay, this function obviously has a parameter, and the parameter has a name named x, and it has a value of x, and this actually happens to be the first parameter in our function. There's a parameter y, and there's a parameter z, and this happens to be the last one. And this allows, and having these calls allows the data dependency tracker to actually associate the values being passed in x, y, and z with these parameter names x, y, and z. The more interesting thing, however, is this thing here. It's called data.get. And data.get does two things. It gets a name here. It has a name y and a value. And this means that, and this tells the data tracker that we just had a read access to the variable named y with the value in y. Data.get simply returns the value that is being passed, so it's neutral, but it saves, okay, in this statement, we just had a variable y being read, okay? And we also see that in this if statement, we also have a variable z that was being read, and we also see that the whole thing was eventually tested. This is how the data dependency tracker finds out that, oh, in this line, y and z were being read, and then this whole thing was used as a test for further statements. This is how it establishes a data dependency between the test in here and the values of y and z being read. So it knows that the test in here depends on y and z. And all of this happens without changing the semantics of the program in any way, because data.get and data.get and the other and data.test all return the values that are being passed. So it's just a simple pass-through of values, regardless of what the values are. The important thing is that we are accessing these things. And so this is already, so you already get an idea of how these control dependencies work, because data.test now saves, okay, everything that follows is going to be control dependent on the test that is set up in this line here. Next thing is data dependencies, and data dependencies are even easier because what we have here is the return statement that actually was executed. And here again, every single read access to the variable is wrapped in a .get call. So we see that y is being read. And for every return statement and every assignment in your program, everything, a value gets set. We have another call to data.set. And data.set says, okay, this named variable here, say the middle return value, is being set here. And since we have all of this in one statement, we can already see, because Python executes one statement at a time, we can already see that in this statement, obviously, there was a variable y that was being read and a variable middle return value being set. Well, and this tells us that we have a dependency between this middle return value over here and the y value down here. So middle return value depends on y up here. And if you want to know where this y came from, well, where did y came from? Well, that's not too difficult to find out because y was set here up here in this parameter. And these dependencies with all this instrumentation, which looks quite substantial actually, is what our instrument tracks. All of these calls here are perfectly neutral. They don't change the semantics of the program at all. So you can take wow, I haven't checked this on arbitrary big programs, but on substantial programs, and the programs just execute as normal. They are a bit slower because of all of this tracking of data accesses, but all of these accesses are being tracked. And this depends, and the reason why this works is because Python executes one line at a time. When we are looking up any of these functions that is being called looks up in which line of the program we currently are. If we enter a new line, then the set of read variables is being reset. Then we track which variables are being read. Then we track which variables are being set. And this is how we can establish a connection between these. So let us show this on a more substantial program. Let's go to our ongoing example. This is a remove HTML markup, which we already have used as an example quite some time. Just for the record, I'm going to give you the source of it. Yes, and to give you the source of it, let me know. That's actually not exactly straightforward. We need an inspect module here, such that we can access the source code. And now we do access the source code. Well, if only we could. I wanted to, so let me do this up here. From bookutils import print content. Here we go. So here's the source code, remove HTML markup. You've seen this a number of times. And this is actually for a change. This is actually the corrected version of the remove HTML markup. So no bug in there to find, but dependencies to look at. So again, we execute. We can take a slicer and execute this function. So we put up a slicer, and we need to specify the function that we want to instrument, because otherwise, otherwise we're not going to have any of these underscore data accesses being done in the background. And we build a slicer here, and we invoke this on some arbitrary HTML input. Here we go. Nothing too complicated. We can still look up individual variables. You see, nothing in the program behavior has changed. And now we can actually look up what is happening here in the program. slicer.code. Here we go. So this is the program code now as it's being annotated, and you see that there's quite a number of dependencies in here, and plenty of things that have happened in here. Interestingly enough, things that are not being executed, things that have no influence. This quote equals not quote. This has no effect, and the assertion also has no effect on the slice. The real nice thing comes when we are actually putting out the graph as is, the hrm slicer. Here we go, and it produces the slice for the slice for this entire function, which again is quite substantial. And let me make this slightly smaller such that more things fit on the screen still. It is a long slice. So we have the return value at the very end. So we have in the end what this thing does, it returns a value named out. And where does this is unconditional. There's no control dependency on out. Where does out come from? Out comes from this statement, and it's precisely this out. Out comes from this statement here before. Out is out plus C. And you can see that this statement actually data depends on itself because the new value of out depends on the old value of out in this very statement. And then the question is, where do these values of out and C come from? We can follow the graph on the right-hand side. Then we'll get to this statement. Initially, out was the empty string. So far, so good. And where does C come from? We follow the dependency on the left-hand side, and we see that C has its origin in this 4C in S thingy. This is where C came from. Then we can now look where this is 4C in S. So where did this come from? We again follow the dependency, and we end up in the original line of remove HTML markup up here. Okay. So all of this is actually pretty simple if you just follow these dependencies. But unfortunately, out is also being data dependent on an earlier test. And these are all the tests that actually happen that actually take place in our program, namely the check that, namely out in the variable C. Sorry, this out is only executed if tag is false. It only depends on the last test. This test depends on the earlier test. This test depends on the earlier test too. And all of these set actually tag to true and to false, which all influence this final test. So in the end, you will still walk through the entire part of the program that had an influence to it, but you can, of course, then select which data dependencies to follow as part of your reasoning. Interestingly enough, there is one setting here, tag equals false, that has apparently no influence at all on anything. It's just listed there in the graph. This is actually being executed, but it doesn't influence anything. And why doesn't this influence anything? This is simply because our input here does not, well, it immediately starts with an HTML tag. And if it starts immediately with an HTML tag, which is the condition up here, if C equals less than, then tag is set to true. And the previous values of tags have actually no influence, say, on this statement or whatsoever. So tag equals false is being executed, but it has no effect on anything in the program. So, and this is how you can make these slices, these dependencies explicit. In the chapter, you're going to find even more complex examples. And of course, in particular, if you have a large program that depends on where you have values that depend on hundreds or thousand variables in the long run, having such a big graph all at once is probably not what you want to see. But if you follow a graph like this incrementally, that is, you start with one value. Say you have this in an interactive program. You start with the last value. You want to know, where does this come from? Where does this come from? Where does this come from? And then you may even be able to jump along. And then you may even be able to jump along in the program code, jumping from one part to the other, and then figuring out where does this come from? Where does this come from? This can be a tremendous help in debugging. So in the actual chapter. The actual chapter is, as I said, is quite massive because also in the end, I wanted these dependencies to work for pretty much everything in Python, which may have been a bit too much. But the nice thing about this slicer is that you don't actually have to fully look into what's going on with all these instrumentations, what's going on behind the scenes to gather all these dependencies. As I said, this is pretty substantial. It even involves generators and yields and asynchronous execution and whatnot. So all of this is included in this in this big slicer. But the nice thing is that you as a user, and you do not have to, because this already encompasses all of Python, you do not have to look into every detail of how the slicer works. This is actually something that you can mostly skip. But what you can do is you can make use of these dependencies as they are produced by the slicer, and then build them into your interactive debugger, for instance. That is, you have a command and you wonder where does this value come from. You can then ask, hey, here's one of these most essential slices. You can then ask, where does this come from? Where does that come from? Where does this come from? Give me a slice of this particular value. Jump to the appropriate location, examine more parts in there, and then you can find out, oh, this value came from here, this value came from there. Oh, this value is not, this part of the graph is not connected to the rest. How come that this value does not flow into anything else? You can even create warnings with that, saying that, oh, you have been computing this value, but apparently this has no influence on anything, which is probably going to be a mistake. Here's y, for instance, in our code, and this y, which we're just having here, apparently doesn't flow into anything. So why is that? Did somebody make a mistake or something? And all of these dependencies, well, all of these dependencies are, of course, dynamic dependencies, meaning that if this value is computed and later not used, maybe it will be used in another run. But you can track all of these things down, and this is where a slice gives you tremendous help in figuring out how individual values came to be and where they came from. So this is already all there is for today. So we have seen slices, we have seen dependencies, control dependencies, data dependencies, how they work. We also have seen how to actually how to almost excessively instrument a program to track all these dependencies, a way to instrument the program that is entirely without effect on the program semantics. So this should actually work on any Python program. The chapter has a section on limitations, but this is really, really small. And this is something that as such is something nice to visualize and nice to follow, but the true power of these dependencies come if they are integrated in an interactive debugger, then allowing you to go back and find out for every single value that you look at, where does this come from and which parts have an influence on that, and therefore helping you in exploring the program semantics and the execution semantics. This is all we're having for today. Beautiful program slicing, rather easy to use. As always, use a with clause and the function the function to execute. Nothing more complicated than that. And of course, there's also a programmatic interface for accessing these dependencies. So not only can you visualize these as graphs or as code, but you can also go and access them programmatically and then integrate them in a tool or technique of your choice. One very obvious thing, for instance, could be to take the statistical debugger, which we have looked at earlier, and think about, wow, in the statistical debugger, we have associated the execution of individual lines with failures, and we found out that, oh, if this line was executed, then there was a particular, this is correlated with failure. And this could also be something that you can use with such dependencies, because you can say, oh, whenever there was a data flow between A and B, there was a failure, and therefore we should focus on these data flows. And maybe this could even be something for security analysis, because if you have a data flow that goes directly from the input to your database without actually checking whether they're authorized to do something, this would actually be an immediate sign of a breach of security violations. And yes, find out this could also be something. This could also be something that you can put into assertions. There should be no flow between A and B, or there should be no control flow between A and B. So the possibilities for combining this with other debugging and analysis techniques are very substantial. With this, I'd like to invite you to have a look at the chapter. We're going to send out the links in a moment. And I already, oh, the sound good. Everybody is saying, okay, good, we get that. Okay. And if you have any questions, now is a good time to ask questions, open questions, anything. And if you don't have any questions,
so right now there are no open questions.
Johannes, do you have any questions?
No.
Today? No questions from you either. Okay. You could ask me, how long does it take to actually build this thing? But no, actually, this was perfectly feasible. I'm very happy that we're doing this in Python and not in C or Java. In C, this takes months to build. In Java, probably a single month at least, maybe two, maybe also 2 months. In Python, it's 4 days of work to get this done and another couple of days to get this debug right. Okay, good. No question from your side? No, nothing, anything? Good. I'm going to send out the link in a moment, as well as the video, whatever. And we're going to see each other again next week. And next week, we're going to go for a super treat, probably the highlight of the entire course, when we'll go into automated repair of code. That is, I'm having a piece of code, and I'm executing it, and I'm throwing up my automated repair, and within seconds to minutes, I automatically get a repair of the code, an automatic fix. How does that sound? I have it running up here. It's pretty cool, and we're going to look at that next week. Thank you very much for your attention, and see you soon, folks. Bye-bye.